So today we're going to be looking at the calculus of variations. So first off, I'll start with a couple of introductory terms for us to be familiar with, go into a little bit of the history, just a couple of key points. Then we'll cover some preliminary topics on normed vector spaces. From there, we'll talk about a few key concepts in the calculus of variations. And with those, we can then derive the Euler-Lagrange equation, and using that, solve the brachistochrone problem. So first off, a functional is a function that maps from some set of functions into the real numbers. So we can kind of think about this intuitively as being a function of functions or a function on functions. A good example here is the arc length functional. So we take the space of once continuously differentiable functions and map it to the real numbers. So if you were to give me some interval and a once differentiable function, I could throw it in there and it would tell me how long it is. And then variational calculus is all about finding the minima and maxima of these functionals using what are called variations, which is kind of a generalized idea of the derivative. And we do this by perturbing functions rather than perturbing real numbers. So usually people consider this field as beginning with Johann Bernoulli in 1696, where he posed and solved this problem asking for the path of least time between 2 points. Wasn't necessarily a new problem, but his solution was the correct one. Galileo had looked at this in the 1630s and said that the arc of a circle is the fastest path between 2 points under gravity without friction. Later on in the 1750s, Lagrange was under Euler, and he pushed for more of an analytical approach to calculus problems, especially in variational methods, over what was more common, which were the geometric methods. So if you look at Bernoulli's actual solution, the brachistochrone problem, it's a lot of geometrical reasoning. And this would be a very fundamental result, or rather, they discovered the Euler-Lagrange equation, which was a very fundamental result, and it's a differential equation, which allows us to minimize and maximize functionals. So some of the key concepts that we need to be familiar with first off is the idea of a vector space. A vector space is a set V with these 8 properties over some field. We're talking about the real numbers here today, and we would just call this a linear space or vector space. So first, we have the set of continuous functions over some closed interval. This is a vector space. If you were to go through add 2 continuous functions, it stays in that space. You multiply by a scalar, it's still continuous, so we're all good. We could then move up another level and say, well, what about the set of once continuously differentiable functions? Well, that also ends up being a vector space. And we denote these with CAB and C1. And we can just take this up to any n and say that the space of n times continuously differentiable functions is CNAB. Now, in order to do analysis on these spaces, we want to have some concept of distance or size. So we say that a normed linear space is a linear space with each element x having a non-negative real number assigned to it, called the norm of x, such that the norm of x is 0 if and only if it's the 0 vector. We have the homogeneity property, so if we have the norm of alpha times a vector x, it's equivalent to the absolute value of alpha times the norm of x. And then finally, a really key one for us with analysis is the triangle inequality, so this holds. And depending on what space we're in, we're going to have different norms. So in the space of continuous functions, we just say that the size of some function is the maximum value achieved by that over a closed interval, the absolute magnitude, of course. So in space C1, then we just take that a step further and sum not only the absolute value the function achieves over that interval, but also its first derivative. And if we had 2 functions in C1, let's say y and z, and they were close together, that would mean that the functions themselves, the 2 continuous functions, must be close together, as well as their continuous first derivatives. So of course, if one of these was greater than epsilon, the sum would be greater than epsilon. So. And then generally in the space Cn, we just talk about the sum of the maximum values achieved by these functions and their continuous derivatives up to the nth derivative. So then from here, we can actually move into some of the more variational calculus specific concepts. So again, if we have a functional that's mapping from some linear space of functions to the real numbers, it's continuous if at the point y hat in this linear space, for all epsilon, there's a delta greater than 0 such that the distance between the output of this functional being is less than epsilon whenever the input vectors are less than delta from each other. And really this looks pretty familiar, just like what we would see in the real numbers, except our domain is a norm linear space, so we consider a norm as our metric. And typically in variational problems, we're going to have inside of the functional some first derivative or higher order derivative of the function. So most of the time we don't actually work in the space C, we work in some space of a higher derivative. Next, if we want to start talking about derivatives of functionals in these spaces, we need to have an idea of linearity. So we say that for some norm linear space V, if phi of h is a functional on this linear space, then it's a continuous linear functional if we can move scalars in and out of the functional. And for phi of h1 plus h2, this is equal to phi of h1 plus phi of h2 for any h1 or h2 in this vector space or function space. And then of course those two are linearity. Third, we just need that it's continuous everywhere. So as an example, if we take this functional phi of h, which is the integral from a to b of some fixed continuous alpha times h, we can just see that this is linear by plugging in beta times h1 plus gamma times h2, where beta and gamma are scalars, and h1 and h2 are functions. And then inside the integrand, we just distribute across our alpha, and then since the integral is linear, we can break this up and just get right back to our beta times phi of h1 plus gamma times phi of h2. So we see that linearity holds. So this first lemma now, we're going to kind of build up some of the foundations in order to lead up to the Euler-Lagrange equation. This one looks pretty unassuming, but it's actually very important for us later on, so much so that it's often dubbed the fundamental lemma of the calculus of variations. And it states that if alpha is continuous over this closed interval, and if the integral from a to b of alpha times h is equal to 0, for every continuous function h such that it's 0 on the boundaries, then alpha has to be 0 over that entire interval. So we prove this with contradiction. So let's say that alpha is non-zero. In this case, we'll just say positive at some point inside the interval. So since it's continuous, there's some subinterval over which it's also positive. And then what we do is we choose our function, since this works for all continuous functions. We use this polynomial function here, h. And since we evaluate this at x1 or x2 and get 0, our boundary conditions are preserved. So we've set this up so that if we take h and plug it into our integral here, over this subinterval, we have a positive function times another positive function, so the area under the curve, of course, is going to be greater than 0, which is a contradiction. So alpha has to be 0. And that's our final proof. Second, we have a very similar one, except here we're talking about h prime. And this is often called the Dubois-Riemann lemma, I believe. And it states that if alpha is also continuous over this interval, and if we have this integral of alpha times h prime equal to 0 for every continuously differentiable h over this interval that's 0 at the boundaries, then alpha has to be constant over that interval. So here we're going to kind of use the fundamental theorem of calculus to help us out. So we say that this constant that alpha will be later is going to be defined by this condition here, that the integral from a to b of alpha minus c is 0. And then we define h to be this integral from a to x of alpha zeta minus c d zeta. That's zeta, right? I'm pretty sure.
Xi.
Xi. So anyway, we know now that we can differentiate this and get a continuous function, so it's in C1. C1. If we evaluate this at a or b, it's going to be 0. So it's satisfying our conditions. And so if we take this original integral here and put in our alpha minus c, we find that we have alpha h prime equal to 0, and that this will evaluate to 0 from our boundary conditions. Yet, if we were to plug in h prime, which we've defined with this integral here, we take the derivative, and we get alpha minus c squared. So two continuous functions multiplied by each other, and the derivative is 0. So we can then take lemma 1 and apply that, saying that that continuous function must then be 0 over that interval. add c to both sides, and we get that alpha is that constant that we kind of defined earlier. So that's the final proof there. And finally, our third one, this is also going to come in handy for the Euler-Lagrange equation. It states that if we have two continuous functions, alpha and beta, and the integral from a to b of alpha times h minus beta times h prime is 0, then for every h in C1, such that it's 0 on the boundaries, then beta has to be differentiable, and its derivative is equal to alpha. Again, we prove this using some handy tricks from the fundamental theorem of calculus. So we define this function h to be defined by this integral from a to x of alpha c, and then we integrate by parts this original part of the function to find negative alpha or negative integral a to b of a times h prime. We take this and plug it back into our original expression here, so we get negative a plus beta times h prime, which we have this continuous function here times a derivative equal to 0. So we find that that continuous function has to be equal to a constant by lemma 2. So we can differentiate both sides of this equation, and since we defined a with an integral by the fundamental theorem of calculus, that just becomes alpha again. And we find that beta prime is equal to alpha over this interval. And it's interesting here too that we never had to assume that beta was differentiable. It just kind of follows from the conditions we established. And that's the final proof there.
So what was the statement again? The one statement?
Yeah. So if you have two continuous functions over this interval, and alpha times h minus beta times h prime is equal to 0, then beta prime equals alpha. And we can choose any h and c1 and get this result. And we'll see that later with the Euler-Lagrange equation. Now, in order to establish a concept of a derivative, we need to start kind of perturbing our functionals and seeing how they behave. So we define what's called the increment of a function to be the functional with the input function plus some perturbation function minus the original functional at that point. And so this looks a lot like what we'd see on top of the difference quotient of the derivative in real numbers. So pretty familiar. And sometimes, I went back and actually changed this. Sometimes you'll see notation where when they're talking about the increment at a point y in this linear space, they denote it as being delta j of h, where your increment or your perturbation function is the only argument. So I guess watch out for that. I thought that was kind of a little unclear at times. And then using this increment, we can define the derivative here. So we say that if delta j is equal to some linear functional phi plus this infinitesimal, where epsilon goes to 0 as the norm of h goes to 0, then this functional is said to be differentiable, and we say that this linear part of this expression is the derivative. So if we perturb this function and we find some other linear functional that approximates it very closely, then that linear functional is our derivative. And we would denote this with delta j of y. So, right. First theorem here then is that the variation of a functional is unique. So we want to establish an idea of how our functionals are going to kind of decay when we take these infinitesimals to 0. So we say that if we have this linear functional and the quotient here phi of h over norm of h goes to 0 as h goes to 0, then phi must be equivalently 0 over that interval. And to see this, let's say that phi of h naught is not 0 when h naught is also not 0. So then we set up this here where we have h sub n equal to h naught over n, and then we have this lambda here which is phi of h naught over h naught, and this is non-zero of course. So then if we take the limit as n goes to infinity of hn, we see that that norm is going to go to 0. But when we actually stick hn into this expression, we can pull the n's out since it's linear, and we find that this just becomes lambda again, which is non-zero. So we need phi to be 0 for this to hold as this infinitesimal decays away. Now, to show that it's unique, let's say that we have an increment and it has two different linear functionals that approximate it, P1 and P2. Then, and we have that this epsilon 1 and epsilon 2 go to 0 as we let the norm of h go to 0. So what this says is that if we subtract these two increments from each other and move the terms over, we get phi1 minus phi2 is equal to epsilon 1 times the norm of h minus epsilon 2 times the norm of h. And since these two are both infinitesimals, these are going to decay away faster than order 1. And so then this difference goes to 0. And if this difference goes to 0, then we can just move one to the other side and they're both equal to each other. When I was reading this, I found that a little confusing personally. I haven't worked with like big O notation a lot. But we say that if we have a function f from R to R, and f is big O of x, or like first order, as x goes to 0, this means that the limit as x goes to 0 of f of x over x is less than some constant. But we don't want this infinitesimal that decays to be bounded by a constant. We want it to go to 0 so that these increment and linear functional are equivalent. So to get this order to be higher than 1, what we need is an infinitesimal of order higher than 1. So as we take this limit, as we saw before, this left-hand side goes to 0, which means that if we have this fraction going to 0, the numerator has to be 0. And then we can move the terms over and set phi1 equal to phi2. Okay, so we have an idea of a derivative, taking derivatives of functionals over function spaces. And now we want to use this to find maxima and minima of these functionals. So we say that a functional j has some relative extremum for some point y hat if the difference between jy and jy hat in some neighborhood around y hat does not change sign. And we say that it's a weak extremum if this holds in a neighborhood defined with the C1 norm. So not only do the continuous functions have to be close to each other, but their derivatives have to be close for this condition to hold. And it's strong if we only need the two continuous functions to be close together for this maxima or minima to hold. From there, we can then set up a necessary condition for maximizing and minimizing functionals, which is that their variation is equal to 0. Seems pretty familiar from like calculus, where we have extremum at points where the derivative is 0. And so to prove this, we recall that the definition of our variation here is the increment equal to the variation plus some infinitesimal, where this decays to 0 rapidly. So we have that for really small norms of h, the sign of this increment will be the same because it's at an extremum, right? So if we perturb it away, the sign stays the same. If you're at the bottom of like a bowl, you're always going up in any direction, and vice versa. So now let's say that the variation is non-zero for some admissible direction h naught. So we're kind of going in the direction of this function, and our derivative is non-zero. Then for any alpha greater than 0, we can say that the variation of negative alpha times h naught is equal to the negative of that variation at that point. And this follows by linearity. We can pull scalars in and out. So we have that for arbitrarily small h, we can make this increment any sign we want. But since we've supposed that it has a minimum, then we have a contradiction, and so we have to have that the variation is 0 in order for this to be a minimum. I honestly found this pretty confusing, the way that he did this. This is from Gelfand and Fomin's book on this subject, and it just didn't really click with me. So somebody on Stack Exchange set this up where they put your increment here, and we say that if we have a minimum, this is going to be positive and this is going to be positive, because we're kind of perturbing this in the direction of h, or in the direction of h naught. We're always going away from the minimum, so it's going to be positive. So our variation here, if we have that greater than 0 from our definition, we're always going to be kind of preserving the sign of this increment. So then what we can do is divide both sides by h here. And we find that since these two are the same sign, that this must be less than our infinitesimal. And if we take this and divide by h again, then what we can find is that the limit as h naught goes, or norm of h goes to 0 of this variation is 0 by what we had proved previously in theorem 1 about how these decay. Does anybody have any questions over that? So from here then, we have this condition that we have to have the variation 0 at a maximum or minimum of our functional. And we want to use this to find the order of Lagrange equation. So we're going to set this problem statement up, and let's say that we have some function of f, or f of x of y and z, and it's continuous with respect to the first and second partial derivatives for all of its arguments. Then for the entire class of functions such that ya is equal to this big A and yb is equal to this big B, we want to find the functional which has a weak extremum between those 2 points. So what we're going to do is take our y and perturb it a little bit around its, or over its entire path. And what we need to preserve the boundary conditions of our original function y is that h is 0 at the boundaries, kind of as we saw before with those integral limits. And so, since we're talking about finding an extremum, we can look at the increment, and we see that we have this functional of y plus h minus j of y. And when we rephrase this as the integral expression of the functional, we have the difference of the original function. And we take this first part, and we use its Taylor expansion around y. And we find that the first term of the Taylor expansion, f of x of y prime, that cancels out. And so we have this first linear term plus some higher order parts of the Taylor series. So we have the partial of f with respect to y times h plus the partial of f with respect to y prime times h prime. So since this is continuous with respect to its first and second partial derivatives, so for y and y prime here, we have a continuous function times h, which is continuous, a continuous function times h prime, which is continuous, and we start to see where lemma 3 is coming in. And we drop all the other higher order terms and just consider the linear part, since we're looking for kind of where a derivative exists. So by theorem 2, the variation here has to be 0, and so we set this integral up and apply theorem, or rather lemma 3, and say that that entire expression inside has to be equal to 0. Let's go back to that again. Or actually, I have it here. So what we said before is if we have alpha times h minus beta times h prime, then beta prime is equal to alpha. And so if we just move this over to the right-hand side, we get alpha, or beta is equal to alpha. So this is a very important result. This is called the Euler-Lagrange equation. And this is a differential equation which allows us to find maxima and minima of functionals, because this must be satisfied for our minimizing function on this functional in order for us to have a minimum or a maximum. And what we can do is we can take this and apply this to the brachistochrone problem. So rather than doing all of this geometric reasoning with chords and circles and stuff like that, we can just use some differential equations. And, oh yes, so from what we've just shown here, we have that a necessary condition for an extremum of a functional is that the function inside the functional satisfies this equation, the Euler-Lagrange equation. So now let's take this and apply this to the brachistochrone. So if I give you 2 points, A and B, and we'll just say that they're at different heights, and I ask you for the path of least time between these two under gravity, where we're neglecting friction, we're going to set this up as a functional. So for convenience, we consider our y-axis down and our x-axis in this direction. So let's start off with some physics here. So we say that A, that we defined as our point earlier, is x1 and y2, and B is x2 and y3. So since we don't have friction here, we can have the conservation of energy. So we just have that the kinetic energy minus the potential energy is 0. We can rearrange a little bit, and we find that our velocity must be equal to the square root of 2 times g, our gravity constant, times the height y. And we define this height y as being the difference between the two. So from here, if we want to find the time that this ball takes from point A to point B, we set up this integral, and we integrate ds over v, which is all of our infinitesimal little distances divided by the velocity, where we've defined these infinitesimal distances as being the square root of dy dx squared plus 1, which looks familiar from our arc length. So when we actually stick in all of our constants that we derived and our y function from the form for velocity, we get that the time is given by this constant times the integral from 0 to y2 of the arc length over the square root of the distance between the two. So we've kind of rearranged here. We said that A is now our origin, just for simplicity, so we can have 0 on the lower bound.
Sorry, v here is speed, not velocity, correct?
Yeah, sorry. So what we've done is created a functional, essentially. And we want to take this functional and minimize it. So we would like to apply the Euler-Lagrange equation, but we can actually kind of pull a neat little trick here, where since this functional is only a function of y and y prime, we reorganize the Euler-Lagrange equation to only depend on those two variables, rather than taking this total derivative with respect to x. So we'll take this equality here, where partial, or rather the total derivative with respect to x of this term is equal to negative y prime times the Euler-Lagrange equation minus the partial with respect to x of our functional. And since we are going to minimize this functional, this must be 0. The functional doesn't depend on x, so this goes to 0. So we find that the derivative of that function there is equal to a constant, or is equal to 0. So when we integrate, the inside function must be equal to a constant. And so this right here, is called the first integral of the Euler-Lagrange equation, and it only depends, you see, on y prime, and then the original functional, which depends on y. So we set these terms up, where we take the partial of our functional with respect to y prime, and we get this expression, and we multiply it by y prime, and subtract off the integrand, and we have this set up to a constant from before. And we take the constant and set it equal to 1 over square root of 2 of a, or 2 times a rather, where a is just some arbitrary constant. And when we take this and solve for y prime, and we integrate, we find that x is equal to this integral here. And we use a kind of tricky substitution where we set y equal to 2 times a times sine squared of theta over 2, where we're now parameterizing this function with theta. And we get that 2 times a times the square root, or times the integral of sine squared of theta over 2 is equal to alpha times theta minus sine theta, or a times theta minus sine theta. And when we use this to solve for y, we find that the curve is parameterized by this function in the x direction and this function in the y direction. So this parameterization is actually the curve called a cycloid, which is if you put a point on a circle and spin it along the axis, this is the curve that that point would trace out. So it's not quite the arc of a circle, as Galileo had said, but it's kind of close. So, and yeah, as I mentioned before, a lot of this is from Gelfand and Fomin's book, and Weinstock's book is called, which is more applied. I don't know how I was able to do that in that amount of time. It's really fast, and I hope some of that made sense. I feel like I kind of lost my point there on that one, but Anyway.
Thank you, Chase. Are there any questions?
So I see you have ghetto and crochet over here.
Yeah, I was
What's
gonna
that
mention
about?
it, and I was like, no, I'm already getting confused.
Okay.
Because this variation, I was reading about these functional derivatives, trying to figure this out. And apparently this variation is more of like a directional derivative, like the Gâteau derivative. And then in analysis 2, we've been talking about like, did I say that right? Yeah, we've been talking about the total derivative on nonlinear spaces, which I found is the Frichet derivative. And so I was trying to figure this out. And some of the people who've written about this put it in terms of Frichet, and some put it in terms of Gâteau, and I don't know, I still need to read about it. But anyway, yeah.
Can you re-explain that cycloid explanation? I don't know what a cycloid is.
Yeah. So if I fix this point here and I want to follow this, and I start rotating this ball and just like rolling it along the x-axis, as this moves, it's going to trace out along the top of the circle as it kind of rolls on the x-axis, and eventually it's going to meet back up like this. Kind of have that long, but anyway, when we parameterize the minimizing function of our time functional before, we end up with this curve. And the fact that the circle traces this out isn't really important. It's just more or less the fact that it was kind of close to Galileo's idea, that it's the arc of a circle. That's kind of what I was emphasizing. What else?
If you like follow a spoke on a bicycle,
Right.
you're kind of tracing the trajectory as that point moves in the tire, that's what that is.
Okay, cool. And you said there was a different proof of this that was just like geometric?
Yeah, if you go back and like look at what Bernoulli did, I haven't read into it too much, but he basically traces out a bunch of lines and kind of breaks these chords of like a circle or something into a bunch of infinitesimals and figures it out that way, which I haven't really parsed that out. I would rather do the differential equations.
Yeah.
But one of the things, and the reason why I'm getting into this is because we're working in this project for undergrads that's kind of exposing them to research, and we're doing a problem about this, but we're looking at, so if you had a ball rolling down a path, but gravity was variable depending on how close it was to some mass, as well as friction along the curve, and then trying to figure out what the solution is. And what I've found is like, people have done numerical ones, but nobody's like tried to actually come up with an expression, if it even exists. So that's kind of what got me into learning more about this. So anyway, yeah. Any other questions?
I just want to make a comment. So with that, not trying to be the guy who's like, what are the applications? But like, if someone was trying to use that where gravity changes, is that more of like a, I work for NASA and I'm trying to figure out some sort of trajectory in space. Is it more realistic that gravity like changes on that extreme of the level?
I don't think it's realistic at all. I mean,
Okay.
it's just kind of like a thought experiment because
Okay.
you'd have to be really, really far away for that to matter.
Oh, sure.
And I don't know if it's, all the different factors of something coming into Earth, let's say, like it's getting pulled in from gravity, it's not gonna really follow this minimizing path necessarily. There's too many other variables. So I think it's just kind of for fun.
Fair enough.
But this field does have a lot of applications. I'm kind of glad that you mentioned that. You can apply this to a lot of control problems and find like the best function that will minimize certain behaviors of a system, and that gets into the field of optimal control, which I'm hoping to use this to kind of lead into, but it'll be a little bit.
So the problem that you guys were working on, was it that you were getting close to like a point mass, or you're getting close to sort of like a horizontal mass, and as you got closer, the gravity increased?
Let's see. I think the problem is that we have kind of like Earth here, and then we're just considering its center and the
Yeah.
distance from the center,
Yeah.
and saying that that center really holds all of our gravity, so like kind of like a point mass, I guess. And then let's say we have some height of this point above the surface of Earth, and we'll say that this is R1, and we wanna come all the way over to R2 here. Then what is the curve that will take the least time under this variable gravity to get from here to here? And then we have to parameterize this with like polar coordinates and stuff, which I was able to work this out without friction.
So it's the least time?
Yeah, so how fast can we get from here to here? Like what path will get us from here to here in the least amount of time?
And you have like, there's like this gigantic line that you draw in space.
Pretty much.
Okay.
Yeah, and it's all 2D and stuff. I think it would be cool to take this and put it in spherical coordinates and like make a thing where you give me a coordinate on the Earth and tell me how high you want to go up, just so you can make it super, super far. Give me another coordinate somewhere else, and then tell me how high you want to go up, and then I find a path that'll get you from there to there in the least amount of time.
Scary roller coaster.
Yeah, yeah. So.
6-7 kilometers.
You have to have like a spacesuit when you get on the roller coaster.
I may be able to, here, let's.
Way going through Earth's atmosphere.
Let's try this actually. So this is what I've been trying to figure out. Is like, this is kind of the path in radius or polar coordinates, where you're starting here and you're coming over to here, and we've normalized everything with respect to that 100,000 kilometers or whatever. Took out all the units, and then we just kind of traced this curve to here. And this isn't necessarily a cycloid, since under that inverse gravity it behaves a little differently. I heard, or I saw somewhere on another paper, somebody saying something about it being like part of a hypocycloid. I'll figure that out later.
There's like a circle rolling in another circle.
Yeah, right. It's like on the, you have a circle on the inside of a circle.
Oh, on the inside. Okay.
Yeah.
Oh yeah, hypo would be hypercycloid.
And then once you put in friction, then you get really nasty like nonlinear differential equations. So I guess go talk to my numerical math professor and get that worked out. He'll know. I won't.
Good luck.
Yeah. But yeah. I guess like we're out of time.
There's a solution to that one. Probably not that high.
No, not exactly.
No,
Are there
yeah.
Any final questions for Chase? All right, if not, let's thank him one more time. Next week, I'm talking.
Mitch again.
Yeah. This is my seminar.
Bye-bye.